Osmosis. I think probably the way people have heard of this the most is if you watch TV, you see commercials for reverse osmosis water purification systems. And that is a valid technique. It's not crazy or anything. But what's osmosis? We're going to talk about reverse osmosis. Osmosis is the flow of solvent from a less concentrated solution to a more concentrated solution. So I think it's fairly common knowledge that if you were stranded out at sea, that you should not drink seawater, right? For one thing, it tastes nasty, but you actually would become more dehydrated by drinking the seawater than you would by not drinking anything at all. Why is that? We say that seawater or any salty water is a thirsty solution. So here's an illustration of your intestinal wall, and this is inside your body, and this is inside your intestines. Have you ever thought about this? The inside of your stomach and your intestines is actually the outside of your body. There's this big hole that goes through you. So this part is actually outside your body, and this is inside. So here are your regular bodily fluids, and here if you have consumed ocean water, seawater, there's a lot of salt in seawater. And what osmosis does is the water, the solvent molecules, will go through your intestinal wall and into the more concentrated solution. So by drinking salt water, you're actually drawing more water out of your body. So let's look at a more scientific, lab example. So here we have a tube. It's shaped like a U, and we used to call these U-tubes. Had a completely different meaning than it does now. Here in the middle is what's called a semipermeable membrane. The cell walls in your body, your intestines, your body is just full of semipermeable membranes. And you wouldn't be able to live if they weren't. A semipermeable membrane is permeable to some things. That's why it's semi-permeable. So it allows very small molecules to go through, and it does not allow large molecules to go through. So this semi-permeable membrane has pores in it that are small enough that the salt ions cannot get through, but they're large enough that the water molecules can get through. So if we take this tube and we have pure water on one side, and we have salty water on the other side, what happens is that the water molecules are going to go overall in this direction. And this really is an equilibrium. Okay, and so having studied equilibrium, we jumped ahead, we can understand this a little better. So if there's a lot of water molecules over here and not as many over here, can you imagine that there's the rate of water molecules going to the left is going to be greater than to the right, just because there's more of them, right? And then as the water molecules overall move this way, the volume over here is going to become greater, and the level of the liquid on this side of the tube is actually going to rise up, seemingly all by itself. It's really kind of crazy to look at because that stuff doesn't happen in regular life. You don't see maybe the aquarium, you don't see just the water on one side of it just like rising up suddenly compared to the water on the other side. It's like that'd be really freaky. Like, what's going on? This is because the water is traveling more in this direction than it is in this direction. And so this side will come up. Now, as this rises, we get a pressure difference here. So this is a little bit like the barometer we studied. The difference in the levels of the liquid on each arm of this tube is a reflection of a difference in pressure. So it will not go up indefinitely because eventually the pressure difference will stop it from rising further. And the pressure difference here, this pressure is called the osmotic pressure. Another way to think of osmotic pressure is it's the amount of pressure you would have to apply to stop the osmosis from happening. Guys, have any questions about osmosis? It's kind of a weird topic and we're covering it very superficially. So the osmotic pressure is a colligative property. Doesn't depend on what those particles are. So if it was a sugar solution or a salt solution, the water would be drawn into it. Do you know what's in teriyaki sauce? You actually don't have to buy expensive teriyaki sauce. You can make it yourself. My husband's Japanese, so we do these things because we sometimes marinate multiple tri-tips in teriyaki sauce. That would be really expensive to buy all those little bottles. It's a third sugar, 1/3 part sugar, and 1/3 soy sauce, and 1/3 liquid of some kind. Depending on who you talk to, you can use beer or water or almost anything. So there's a lot of sugar in it, and there's a lot of salt in it. So high molality in the teriyaki sauce. We don't eat these as much anymore, probably because our income is higher. But when we were in graduate school, after we first got married, we would sometimes have teriyaki hot dogs for supper. And they're actually really good. So you just run a knife and you score the hot dog a little bit and you boil it you cook it in teriyaki sauce. And you eat it over rice and it's actually amazingly good. Well, my husband was working late and so I left his hot dogs in the teriyaki sauce just to, so they wouldn't dry out, I thought. I wasn't thinking. I was a chemist, but I wasn't thinking. By the time he came home, those hot dogs were as hard as a rock. Okay? Because hot dogs, like a lot of food, it comes from living things, right? It's got semipermeable membranes. So here I have this hot dog. Hot dogs are salty themselves, but here it is soaking in a sugar salt solution, drew all the water out of those hot dogs. Osmosis in the kitchen, okay? It happens. If you're marinating meat, the recipe will say to marinate it for so many hours. You don't want to do it longer than that. Longer is not necessarily better. It'll probably draw too much water out of it. When you're frying vegetables that have too high of a water content and they make a mess in the oil, if you soak them in salt water, it'll draw some of the water out, and then when you fry them, it doesn't spatter as much all over the place. So osmosis is actually something that we make use of quite a bit, but we just don't think about what's going on there. But it doesn't depend on what the solute particles are. It just depends on their concentration, how many of them there are. So this has a lot of implications in healthcare. Here's some pictures of red blood cells. And here are three words that you may have heard in biology class. They're definitely used in medicine. Your book uses a slightly different word, and I'm not going to quiz you on these, but I just think it's kind of general information. Isotonic, hypotonic, hypertonic. So these prefixes, iso means the same, hypo means less than, and hyper means more than. So an isotonic solution has a solute concentration that's equal to the solute concentration in the other thing. So here we're looking at blood cells. And if they are in an isotonic solution where the concentration of solutes in the fluid that they're soaking in is the same as the concentration of solutes inside the blood cell, then they're fine. If we soak them in pure water, a hypotonic solution where there's less solute, here with water, no solute molecules, there are solute molecules inside the blood cells. And if you can't remember which way does the solvent go, it's trying to make things equal. It's trying to equalize the concentrations. It can't necessarily do it, but it's going to try. And so the concentration of solute inside the red blood cells is higher, and so the water will be drawn in. This causes the red blood cells to swell, and they will eventually burst. You think that would be a good thing to have happening in your veins? No. That's why when they give you an IV in the hospital, it's a 0.9% sodium chloride solution, because that is the molality of the fluids inside your body cells. And so it's isotonic, and it doesn't cause your cells to swell or to shrink. Because over here, if you put the blood cells in a salty solution, in a more concentrated, a hypertonic solution, then it draws the water out of them, and they shrink up and shrivel. And that's not a good thing either. So that's the end of the chapter. Those are skills that you should be able to do.